Professor Salman Beigi from Institute for Research in Fundamental Science, IPM, and also with Phanous Research and Innovation Center. Professor Beigi received his PhD from MIT under the supervision of Professor Peter Shor. Before joining IPM, he was a postdoc at Institute for Quantum Information at Caltech. Today, Salman will teach us about correlation measures with the tensorization property. By this, I hand it over to Salman. The stage is yours.
Okay, great. Thank you for the invitation. Today, I'll be talking about correlation measures with the tensorization property. You all have some sense of what the correlation measure is, so I should first focus on the tensorization property. And to do that, I will start with some motivating examples. I will give you some problems in which you will realize the need for some measures of correlation with certain properties, which will be called the tensorization property. The first problem is the problem of non-interactive distribution simulation. So here we have our celebrities, Alice and Bob, and they are shared with some bipartite distribution, PAB. And we will be assuming that A goes to the Alice side and B goes to the Bob side. And so Alice doesn't know what B is, and of course, Bob doesn't know what A is. And here we are assuming that Alice and Bob are shared with IID copies of this PAB. So they are not having just a single copy, but NIID copies where N is some arbitrary number. They can choose N as large as they want. And then they apply some functions on their input. So Alice applies some function on A1 to AN, which I denote by this phi of A sub N. And the output would be denoted by X hat. Bob applies some function on B1 to Bn. The output would be denoted by Y hat. Then X hat and Y hat have some joint distribution. The goal of Alice and Bob to apply these functions in such a way that the joint distribution between X and Y hat to be the same as some target predetermined distribution Q. So the source distribution is P and the target distribution is Q. From the source, they have N copies where R could be arbitrarily large, and they want to generate only a single copy of the target. This is the important part of the problem. From the source, they can use as many copies as they want, but in the target, the goal is to generate only a single copy of the target. Here, you see the problem set of in text. As I said, AN, BN is NIID copies of some joint distribution PAB. And then there's no interaction is allowed during the computation. During the protocol, they can, of course, start with fix some strategy before starting the protocol. But after receiving these A's and B's, they cannot communicate. And then they apply some local functions, this phi and psi, to generate X and Y hat. The goal is that the joint distribution between X and Y hat to be equal to a target distribution, which is again fixed before the starting of the protocol. Let me give you an example. Suppose that the source distribution is this guy here. As you see, the probability. So here it means that the probability of A being 0 and B being 0 is 1/2. The probability of A being 0 and B being 1 is 1/4, and so on. So this is a source distribution, and here is a target distribution. So the target distribution, A and B are both 0 with probability 1/2, and they are both 1 with probability 1/2, and they are 0 on 0, 1, and 1, 0. So the target distribution is essentially a perfect shared randomness between Alice and Bob, because with probability like 1/2, both of them receive 0. With probability 1/2, both of them receive 1. But the source state is kind of noisy. It gives a positive probability to any pair of 0 and 1. And the question is, can we transform under these local operations, phi and psi? Can we transform NIID copies of P, where N could be as large as they want, to a single copy of Q. And you can convince yourself that this transformation is impossible, essentially because of this structure of this target distribution. The point is that let me try to give you an argument. So look at the Alice side. On the Alice side, Alice receives some n-bit string and then outputs a single bit, either 0 or 1. Half the time, she should output 0. So there exists some strings, A1 to AN, for which phi of that string is 0, right? And then now look at the Bob side. So fix that string on the Alice side and then look at the Bob side. The point is that on the Bob side, the probability of any output, any n-bit string on the Bob side is positive, because on the source, I have all of these things are positive. So any string is possible here. Now, if I look at the output, because I know that because I fixed the string of Alice in such a way that the output is 0, Bob has to output 0 always, because the probability of like 0, 1 is 0. So output, when I fix the input of the Alice to correspond to this output 0, the Bob has to output 0 as well. Now, in that case, because as I said, the probability of any B1 to Bn here is positive, it means that Bob has to, that the function of Bob should be like constant 0, should always give output 0. But it's a contradiction, because we know that half the time Bob should output 1. So maybe my argument was a bit hard to follow in words, but essentially because we have these zeros here, and we can decompose the space of output so that we have a 1/2, and then like if Alice's output is 0 is here, then Bob has to output 0, and then we have a 1 that are separated with the zeros here, then we have this impossibility result. But what if instead of 0 here we have like epsilon, like 0.1, and then these are like 0.4, something like that. In that case, we can this argument that I just told you doesn't work. Let me give you another example, which would be more interesting. Let's say P of lambda. So these are the family of joint distributions. So P of lambda is 1 plus lambda over 4 when A and B are both of them are 0. If both of them are 1, they are 1 plus lambda over 4, so the same number. And here on the off diagonal, I have 1 minus lambda over 4. So if lambda gets larger and larger, you will see more correlation here. For example, if lambda is equal to 1, the extreme case, this distribution would be just this joint like perfect shared randomness that we had in the previous slide, because this off diagonals would be 0 if lambda is 1. If lambda is 0, the other is extreme case, the joint distribution would be the uniform distribution over 2 bits. So it's like there is no correlation between Alice and Bob. It's the same as Alice tossing a coin by herself, and Bob do the same. So there wouldn't be any correlation between Alice and Bob if lambda is equal to 1. So the larger lambda gives me more correlation. Now, here's the question. I want to start with a smaller lambda.
My apologies.
Okay.
There's a question coming up. Sure. Could you take a moment? It says, are these joint probabilities shouldn't be 1/6 and instead 1/4?
No, it should be 1/4, because if you sum these numbers, you would get 1, right? Because this plus lambda cancels this minus lambda, and then we have 4 1/4, and we get 1. So the normalization is correct. Okay. So as I said, so the larger lambda gives me more correlated distribution. The question is that, can I start with a source distribution with a smaller lambda and then transform it to a distribution with a larger parameter, which is denoted by mu. So lambda is less than mu. I have n IID copies of the source, P of lambda, for which lambda is smaller, and I want to generate only a single copy of mu. The question is whether it's possible or not. And as you see, for like general values of lambda and mu, there is no zero probability. So the argument that I had in the previous slide doesn't work. Okay. Now I want to give you a measure of correlation and then see what happens if I want to prove the impossibility of this transformation of this example for that distribution. And the measure of correlation I want to talk about first is the mutual information. This is the first measure of correlation that we learn in information theory. Just to remind you, the entropy of some distribution, so some random variable A with distribution P of A is the minus sum of PA log of PA. And then the conditional entropy of A given B. So here I'm assuming we have a joint distribution, PAB. And then the entropy of A given B is just the average entropy of A when I fix a value of B. To this, in this Venn diagram, the red circle is, I can think of it as A and the blue one as B. The entropy of A is the whole circle, and the entropy of A given B is the part that has no intersection with the B. So this is red part here. And then the mutual information is this the region in common between A and B. And this is like the whole circle minus this part. So I have the entropy of A, which is the whole circle, minus this conditional entropy, which is this part. So this gives me the common part here. Or you can just rewrite it as the entropy of A, the whole circle, the entropy of B, this blue circle, minus the entropy of the joint, which is like the union of these two circles. And if you compute it, you would get this joint part here. So the mutual information is really this, like it's in some sense the common part between A and B, and it can. So this is probably a good measure of correlation. Okay. What do I mean by measure of correlation? To be formal, I'm saying that a quantity or an invariant of distributions or any kind of source in information theory is a correlation measure if it satisfies data processing inequality. So suppose I have this A and B, a joint distribution, and then I apply some functions on A and B separately. So these are, so I'm talking about functions, but you can all over the talk, assuming that these functions are also stochastic functions. But thinking of them as being functions is enough in this talk. So I'm assuming that like Alice and Bob locally manipulate what they have, like apply functions or local functions on their sources. And then we have this data processing inequality. The mutual information between A and B is an upper bound on the mutual information between X and Y. So by local processing of the data that Alice and Bob have, they cannot increase their mutual information. During this talk, I also use this notation. This is a mark. This means that X, A, B, Y forms a Markov chain, which essentially means that X is a function of A and Y is a function of B. And as I said, this is called the data processing inequality. And the proof is essentially is based on the convexity of X log X function, because in the definition of entropy in mutual information, we have this function of X log X. This is a convex function, and that's why you would get this inequality. And exactly because of this inequality, I'm saying that mutual information is a correlation measure, because I cannot increase it under local operations. So you can think of it as a monotone measure of correlation. It's a monotone under local operations. These are my local operations, and I cannot increase mutual information under local operations. So whenever I say that the correlation measure, I mean something that is monotone under local operations. Okay, so this is the data processing inequality. This is one important property of mutual information. The other important property for me is the additivity property. additivity property. If I compute the mutual information between n copies of A and n copies of B, I would get n times the mutual information between A and B. Again, this is a simple computation to verify this using the definition of the mutual information. And the point is that inside the definition of mutual information, I have this log function. When I have IID copies, it means that like the joint distribution is a product, and then the logarithm turns the product into the sum. That's why I get this n times the mutual information. Okay, so now let's use these two properties to see if I can get something for this non-interactive distribution simulation problem. Alice and Bob start with this n IID copy, so I can write down the mutual information between A and B, AN and BN, and then they locally manipulate them to produce this target distribution XY, QXY. Then by the data processing inequality, the mutual information between AN and BN is an upper bound of the mutual information between X hat and Y hat, and you can think of X hat as Y hat being the same as like Q of XY. The distribution comes from QXY. On the other hand, by the additivity problem, this guy here is equal to n times the mutual information between A and B. Now, assume that the mutual information between A and B is non-zero. It's like it could be like a tiny positive number. Because n was an arbitrarily large number, Alice and Bob could choose n to be arbitrarily large. N times the mutual information grows as much as I want, and then this inequality would be satisfied. So my point is that because the mutual information is additive and it increases as I increase n, the number of copies of the source, this inequality would be satisfied, no matter how much it's the correlation, the mutual information and the target. So mutual information, exactly because of this additivity property, does not give me any bound on this non-interactive distribution simulation problem. Okay. So what kind of measures of correlation can I use for this property? These are the measures of correlation that do not have this additivity property. Or to be more precise, I want a measure of correlation that does not scale to infinity when I increase n. Okay, so by increasing n, if I go to infinity, then this inequality would be satisfied. So I should look for measures of correlation that do not have this property, do not scale. In particular, they should not be additive. Or I can go wide and ask, is there a measure of correlation which satisfies this? So I like to have a measure of correlation for which, if I compute the measure on n copies, I get the same number as if I compute it on a single number, a single copy. Okay, and this is called the tensorization property. Like it's the opposite side of the additivity. In the additivity, the correlation scales linearly, and in the tensorization property, it does not scale at all. I get exactly the same number as if I compute it on a single copy. Okay, so that's called the tensorization property, and having the data processing, meaning that if it's a measure of correlation and the tensorization property, I could prove bounds on this non-interactive distribution simulation problem. Okay. Let me go to the second problem. The second problem is just a quantum version of what I just told you, which I'm calling quantum local state transformation. You replace the joint distribution PAB with a bipartite density matrix sigma AB, and then as before, the A parts go to Alice and the B parts go to Bob, and then apply some Alice and Bob apply some local quantum operations. The question is that can they generate a single copy of the target quantum state mu out of sigma? Again, these are independent copies. The number of copies are arbitrary. They can choose n as large as they want, and they want to generate only a single copy of the target. But the same kind of reasonings to prove bonds on this problem, we need quantum measures of correlations with the tensorization property. The question is that do we have such a bond, such measures or not? Okay. The third problem is about channel simulation. So the previously two problems were about sources. Here I'm talking about channels. So by channel, I mean something that has an input and output. The channel could be either classical or quantum. And here it stands for the noise. So in general, the channel introduces some noise to the input and produces output. As before, this is my source channel, this N, and I'm assuming that instead of one copy of the channel, I can use the channel as many times as I want. So this little n is the number of channels. Now think of like Alice want to send some message to Bob. Okay, so Bob is here and Alice in here. The message is X. Again, the message could be classical or quantum. So what Alice can do, she can encode the message inside the n copies of the input of the channel, of the noisy channel that they have here. So AN and A1 to AN. And then she feeds the inputs to the channel, Bob gets the outputs, and then Bob performs some decoding map and produces this output Y. So mathematically, I have this channel, this encoding. This is followed by n-fold tensor product of the channel with itself, this noisy channel, and then I have a decoding which produces this Y. So the concatenation of these three channels would be a channel from X to Y, which I'm calling M. So in the problem, N and M are fixed. So N is my source channel, N is my target channel. And the question is that, is there some integer number, little n, and encoding and decoding maps such as this concatenation is equal to my target channel n? Okay. Again, I have the same sort of phenomenon. I mean, I'm assuming that n, the little n, the number of noisy channels are arbitrary. They can choose as many copies as they want, but their target is, their goal is to generate only a single copy of the target channel. Okay, so m and n are fixed. And the question is that can I choose n, e, and d such that this equality holds? That's this version of this channel simulation problem. Now, maybe the first question is that, is it really a non-trivial problem or not? In some cases, it's a trivial problem. Suppose that n has a positive capacity, either classical or quantum. What does it mean? It means that by n and this scenario, I can simulate the identity channel. Let's say the 1-bit identity channel or 1-qubit identity channel, single qubit identity channel. And because I can simulate or at least approximately simulate this identity channel over a single bit or single qubit, I can use the identity channel itself to simulate any other channel. I can introduce more noise to the identity channel to simulate any other channel. So if the capacity of n is positive, I can simulate the identity channel out of that, and then use that identity channel to simulate any other channel. So in that case, if the capacity of n is positive, the problem is not interesting. The answer would be trivial. We can always simulate any other channel using n. But what if the capacity of n is 0? Okay. In this case, I'm going to consider two subcases, whether the channel is classical or quantum. If the channel is classical and its capacity is 0, then the channel is trivial. If you know about the Shannon's theorem, the capacity of a channel is 0 if and only if the output of the channel has nothing to do with the input. It's like the channel ignores the input and then produces something random as the output, or something fixed. It doesn't matter. So the point is that the output of channel is independent of the output of the input. In that case, there is absolutely no correlation between the input and output, in which case we cannot simulate any non-trivial channel. So with zero capacity, in the classical case, with zero capacity channel, we can simulate only zero capacity channels, which are again trivial. Their output has nothing to do with input, and without sending any message, but Alice and Bob can simulate, of course, a channel whose output has nothing to do with the input. So this question for zero capacity classical channels is trivial, again trivial. But the non-trivial case is when the channels are quantum and their capacity is 0. So I'm assuming that both my source channel N and the target channel M have 0 capacity and they are quantum channels. Okay. And the point is that we have non-trivial quantum channels with 0 capacity. By non-trivial, I mean there are quantum channels for which the correlation between their input and output is non-zero, yet we cannot use that correlation to produce a communication channel, a quantum communication channel, I should say. Let me give you an explicit example. So here E stands for erasure. I'm considering the erasure channel with parameter P. And what it does, given the input sigma, this is a density matrix, with probability P, it erases the input. So it says that, so essentially it sends the input to the environment and says, tells the receiver of the channel that I erased the input. And the probability 1 minus P, it gives the input without touching it. Okay. So with some probability, it erases the information, and with some probability, it just gives the input without introducing any noise. And now the point is that if P is greater than 1/2, the quantum capacity of this channel would be 0. Why is it the case? Because of the no-cloning theorem. Think of P is equal to 1/2. Then and then think of the output of the channel and the environment. So the output of channel with probability 1/2 would be erased, and with probability 1/2 would be just the input. And it's the same for the environment. Whenever the output is erased, it's the erasure flag, the environment gets sigma. Right, and the other way around, when the output of the channel is sigma, it means that the environment receives the erasure channel. So it's a symmetric. So there's a symmetry between the output of the channel and the environment. Now, if the output of the channel can encode some quantum information, environment can do the same. She can do the same thing, the same decoding as the output, and then produce some quantum information about the input. So this means that whatever quantum information is here in the input, both the output of the channel and the environment can decode it. But by the no-cloning theorem, a quantum information cannot be decoded by both by two independent parties. That's why the capacity of this channel is 0. The quantum capacity of this channel is 0. Okay, so we came up with the family of quantum channels for which the quantum capacity is 0. Now we can ask this question that we had in the previous slide: given an erasure channel for a larger parameter P, for a larger erasure parameter, and the copies of that, can we simulate a single copy of an erasure channel with 0 capacity, but with a better parameter? So here, both Q and P are in the range in which the quantum capacities are 0, but the P is a worse parameter. It has more probability of erasure. And the question is that, can I use n copies of the of the worst channel to simulate a single copy of the better channel. Okay. And again, it has the same nature as previous examples, because and of the source, I can use as many copies that I want, and the target I wanna simulate only a single copy of the target. Okay. And my last problem is called the most informative bit conjecture. It's the following setup. So PFAB is the same distribution I considered before with this parameter lambda. Again, A or copies of A are go to Alice, and copies of B go to Bob. And then Alice applies some function on her input AN and to produce a single bit. So here I'm assuming that X is a single bit. That's important. So Alice receives N bits and then applies a function to produce a single bit. And now the question is that what is the mutual information between X and Bob's inputs Bn? I want to find a function phi for which this mutual information is maximal. And the question is that what is the best choice for phi? And the conjecture is that the optimal phi is a dictator function, meaning that phi ignores all copies of A, except the one of them, let's say the first one, and then also the first. So the best function is okay, the dictator function. Again, as you see, n is arbitrarily large. The point is that if I choose phi to be this dictator function, this mutual information would be, this maximum would be independent of n, this number, because it's just would be the mutual information between a single copy A1 and B1, because the other copies for the dictator functions, the x would be independent of other copies. It would depend on only the first copy of B. So for dictator functions, this maximum would be independent of n and would be just a mutual information between A and B for this distribution. And that's why you see this phenomenon of tensorization. You can also verify that, again, this mutual information doesn't give any bound on this, I should say non-trivial bound on this problem, because if I want to use the data processing of mutual information, I would get n times, like the mutual information between X and Bn would be at most mutual information between An and Bn, and that's n times the mutual information between A and B. So it escapes as n increases. So that's why, again, if I have a measure of correlation that satisfies tensorization, it would be helpful for this problem. Okay, so just to summarize these motivating examples, in information theory, we usually ask about the optimal rate at which we can transform a source to a target. And when we talk about rates, it means that additive measures of correlation would be useful for me because they scale linearly as I increase the number of sources or the number of targets. But sometimes even generating a single copy is non-trivial. Okay, in that case, I'm not asking about the rate at which I can transform resources. The first question in the second category of problems is that whether is it possible to generate only a single copy of that. If I can generate a single copy, then I can probably ask about this problem of rates and things like that. And for these kind of problems, this tensorization property would be important. In the second type of problems, when I talk about rates, additive measures of correlation would be important. For the second types of problems, the tensorization property would be a key tool. And you saw some examples. It's not in interactive distribution simulation, the quantum version, which is the quantum localized state transformation, and the simulation of zero capacity channels and so on. The point is that when I'm talking about the rate at which we can transform resources to each other, probably the target, my target is of the same nature as my source. But sometimes the target is completely of a different nature than the source. And this tensorization property is going to somehow capture this nature. It kind of gives me, okay, the nature of this target is completely different than the nature of this source, so you cannot transform them to each other. Why such a measure of correlation with the tensorization property is going to capture this nature? Because it doesn't care whether you have one copy or you have lots of copies. It doesn't care because you want to capture the nature of that source, not the quantity of that. Okay, that's why this tensorization property would be important for these kind of problems. Okay, maybe it's a good time to stop here and then ask. You can ask questions, and then I would give you the first example of a measure of correlation with the tensorization property.
There's a question concerning the notations. I think it has to do with the previous slide. It says, is small a and b and capital A and B same in all conditions or not?
Well, yeah, thanks for asking. So by little a, I mean some elements. So by capital A and capital B, I mean the corresponding random variables. And by little a and little b, I mean realization of that. So whenever I say capital A, I mean, I'm thinking of the random choice of A and B. And whenever I have this little a and b, I mean a single realization of the random. So here, like little a is either 0 or 1. Little b is either 0 or 1. I hope that answers this question.
So I'm guessing we don't have further questions.
Okay, great. Okay. So yeah, so I gave you this motivating problems, and then I'm going to give you the first measures of correlation with the tensorization property, which is called maximal correlation. To give you the definition of maximal correlation, I start with something called the Pearson correlation coefficient. Suppose I have this joint distribution that I had before, and suppose always apply some function here. F is a real function. So it takes some little a and then produces some real number. And then similarly, Bob receives some little b and then produces g of b to be a real number. And then the Pearson correlation coefficient between f and g, these real functions, would be the normalized covariance between f and g, which is defined in this form. So this square root of this product of variances is the normalization. And then this is here I have this covariance. So I fix first shift f and g by their expectation to center them, meaning that to make their expectation to be 0, I consider their product and then compute the expectation of the product. So this is called the Pearson correlation coefficient because of the Cauchy-Schwarz inequality. This Pearson correlation coefficient is some number between -1 and 1. The point is that here, in some sense, you can think of this expectation of the product as the inner product that between this function, the center function, and this center function. And then the inner product between two functions is at most the product of their norms, and their norms are appearing here. The square root of the variances are essentially their norm of the center functions. And that's why it can apply the Cauchy-Schwarz inequality and realize that the Pearson correlation coefficient is at most, its absolute value is at most 1. And now, what's a maximal correlation? It's the maximum of the Pearson correlation coefficient over all choices of function f and g. So I take various choices of f and g, compute their Pearson correlation coefficient, and then try to maximize it over all choices of f and g. Here's a formulation of the maximum correlation. So I denote the maximum correlation by rho. Rho of AB is the maximum correlation between A and B. This is, as I said, is the maximum of the correlation coefficient between f and g. Here I normalize f and g. I just scale them so that their variances are 1, and then I shift them, center them to make their expectation to be 0, take the product, and then compute the expectation. So that's the definition of maximum correlation, or you can assume that the expectation of f and g are 0 from the beginning, and then that would be the definition. So you are maximizing over all functions f and g. F is a function of a real function of a. G is a real function of b. You maximize over all choices of these functions with 0 expectation and unit variance. And you take the product, I take its expectation, and maximize. Okay. So that's the definition of maximum correlation. What were the properties? Again, by this Cauchy-Schwarz inequality, this maximum correlation is at most 1. And it's a positive number because you can, for example, replace f with minus f. So the minus side of the this interval -1 to 1, you can ignore that. The maximum correlation is some number between 0 and 1. In f, if f and b are independent, meaning that their distribution is multiplicative, then the maximum correlation is 0. Why is it the case? Just look at the formula. The expectation of fg is because it's a product distribution, it would be just the expectation of f times the expectation of g, and that's I know that the expectation of f and g are 0, so that's why the maximum correlation would be 0. The other thing is that it's really a measure of correlation, meaning that it satisfies the data processing inequality. If I apply some function of a, generate x, some function of psi on b, generate y. In other words, if I have this Markov chain condition, then the correlation between the maximum correlation between a and b is larger than the maximum correlation between x and y. Why is it the case? Because if I want to compute this maximum correlation between x and y, I should maximize over the choice of functions of x and functions of y. But remember, if I have a function of x, x itself is a function of a. So I can think of a function of x as a function of a. So if I want to compute this maximum correlation, it's the same as restriction. I mean, considering this definition of the maximum correlation of a and b and restricting f and g to be not only a function of a and b, but also functions of x and y as well. So that's why, by the very definition of this maximization over functions, I have this data processing inequality, and we can prove data processing inequality with other methods. I'll show you later, but you can see from the definition, it's clear that it's really a measure of correlation and satisfies the data process. Okay. Now, in this slide, I want to give you another formulation of this maximum correlation. So suppose I have these functions fag as before. In this definition of maximum correlation, I have expectation of fg. I want to rewrite this expectation of fg, which is an expectation over my random variables a and b, in this form. I first take the expectation over, I first fix b and then takes the conditional expectation a given b and then take average over the choice of b. Okay. This thing, if you're not familiar with this kind of notation, it just means this one. So the expectation over AB, I have like a summation over PAB times f of A, G of B. I'm rewriting PAB as P of B times P of A given B. That's the meaning of this thing here. But then I noticed that B is independent of A. So this second sum here, I can just put it in the parentheses. In the notation here, it means that I can move this second expectation here inside this parenthesis here, and then rewrite it as the conditional expectation of F times G. And then I have, of course, this expectation over B on the outside. And now I can apply the Cauchy-Schwarz inequality. Here I have a function of B. Remember what I do here. I fix a value for B. Okay, it induces some distribution on A, some conditional distribution on A, and then I take the average of F over that with respect to that conditional distribution. And then this whole thing here would be a function of B, like the one here. So here, this is a function of B, because B here is like the argument of this function. If I fix B, I have this conditional distribution, then sum over A, I get some number which depends on B. So this guy here is a function of B. So I have two functions of B, I multiply them and then take the average. Now, again, I can apply this Cauchy-Schwarz inequality. What it tells me that the inner product of this function and this function is at most is the norm of this function times this function, which means that what's the norm is a square root of the expectation of the first function squared times the square root of the expectation of the second function squared. That's the Cauchy-Schwarz inequality. Now, in the Cauchy-Schwarz inequality, I have equality if and only if these two functions are parallel to each other. They are proportional to each other. In that case, I would get equality. Okay, what does it mean? It means that if I fix F and try to find the optimal G, the answer would be a G that is proportional to this function here. So if I fix F and compute this conditional expectation, I get a function of B. And then this Cauchy-Schwarz inequality tells me that the best G that I can choose is some number times this guy here. Okay. So by G star, I mean the best function, the optimal function for the choice of F. So as I said, this is some number times this one, and this number is chosen here so that this variance condition is satisfied, so that G star is normalized. So I can rewrite this for this choice of F. I can rewrite this optimization problem in terms of an optimization problem in terms of a single function F. Okay. Now, as I said in the previous slide, you saw that this conditional expectation operator is something important. Okay, so let me give it a number, give it a notation. So here by this calligraph f of A, I mean the space of functions of A, and this calligraphic fb, I mean the space of function of B. And then you realize that I can think of this expectation as an inner product on the space of all functions. And then I can think of this conditional expectation as an operator from the space of functions of A to a space of function of B. If you give me such an F for a value of B, T of F at point B is the conditional expectation of F, where the conditional expectation is with respect to when I fix B, I have some induced distribution of on A, and then I can take the average. Okay, this is the same operator that I had in the previous slide. I just gave it a name, T. And this operator T, you will see that it would be important during these lectures. You will see it several times. Okay. Now, so this is an operator. This is a matrix in general. If A and B have finite alphabets, which I assumed during this talk, then I can think of this first singular value of this matrix. So S of 1, the singular value, by definition, it's I sandwich T with two vectors, F and G, and then I normalize the vectors. I normalize this quantity or the choice of these vectors and maximize over F and G. That's the definition of the first singular value of T. And now I can expand this. So what's T of F? By definition, it's just it's this conditional expectation, and then I have this expectation on the outside, and then here I have these norms. Of course, the norm are with respect to this inner product. So it would be the norm of F would be the square root of the expectation of the F squared, and similarly for G. So I'm just rewriting this. And you saw in the previous slide that the expectation of G times this conditional expectation is just the expectation of F times G. Okay, it's just the computation that I had in the previous slide. Remember, let me go back. Yeah. So this guy here is equal to this one. Okay, and this one is T of F. Okay. And again, by the Cauchy-Schwarz inequality, that's most one. Right, the inner product between F and G. This is the inner product essentially, and then I have norm of F, norm of G. So this is at most one. This means that the first singular value is at most one. But if I let F and G to be the constant functions F to the constant function with value one, then this would be an equality. By constant function, it's a function that always outputs one. So F of A is equal to 1, F of G of B is equal to 1. The product of F and G in that case would be just 1. The expectation of this single number 1, constant function 1 would be just 1. Also, these things on the here would also be 1, and then you get the equality here. Anyways, we see that the first singular value of T, this operator here, is 1. Okay. So this is not interesting. It doesn't capture anything about the starting distribution P A and B. So let's think of the second singular value. So what's the second singular value? The second singular value would be equal to the same maximization problem, but I should restrict F and G to be orthogonal to the vectors associated with the first singular value. So it's the same optimization problem, but I'm restricting F and G to be orthogonal to these functions that I obtained for the first singular value. And what's this inner product? We have this formula for the inner product. The product of F and the constant function would be just F. So the orthogonality is nothing but the expectation of F being 0. And the second orthogonality condition is the expectation of G being 0. And what are these norms? If you think about that, when the expectation of F and G are 0, the expectation of F squared is nothing but the variance. So I have this variance condition. That's a normalization. I'm removing this norm of F and G from here to just write the expectation of F and G. So that's why I added this condition, the normalization of the variances. And here the objective function would be just the inner product of G and T of F, which is nothing but the expectation of F times G, besides here or in the previous slide. And that's, if I remember, that's a definition of the maximum correlation. Okay, so what we learn in this slide is that the maximum correlation between A and B is equal to the second singular value of this operator T. Okay. Okay. Now, using this characterization of this maximal correlation, I can prove other properties of maximal correlation. So this is the same thing T that I had before. That's the definition of T. And then by computation, we saw that it's equal to the second singular value of t is equal to the maximum correlation. Now let us compute the second singular value of t tensor itself. Okay, the singular values of the tensor product of two matrices come from the product of the individual singular values. So the largest one, the largest singular value of t tensor t would be the multiplication of the largest singular value of t with itself. Okay, so I take the maximum singular values and multiply them together, I get the maximum singular value of t tensor t. And this is 1 because S1 of t, we just saw that this is equal to 1. So the maximal singular value of t tensor itself is 1, not a surprise. What about the second singular value? The second singular value of t tensor t comes from the multiplication of the first singular value of t and the second singular value of t. Okay, so think of like sorting the singular values of t and then multiply them together. The largest one, the largest multiplication comes from the multiplication of the largest pairs, and the second one comes from the largest one with the second largest one. So that's why the second singular value is S1 times S2, and in fact it has a multiplicity because you can choose S2 from the first one and S1 from the.
May I interrupt with a question?
Sure. Mm-hmm.
There's a question. So is there any sense in considering further singular values? Like, would there be any meaning to the third singular value?
Yeah, sure. You can prove, I guess you would see in the next slide that the second singular value, you can actually prove the data processing inequality using this formulation that the maximum correlation is the second singular value. And you can use this similar kind of reasoning to say something about other singular values. But the point is that here I'm interested in the tensorization property, and the tensorization property holds only for the second singular value. And that's why I'm focusing on second singular value. But as you can guess, the other singular values are also meaningful.
So does it mean that by the first and the second, we mean the first larger and the second largest?
Yes.
Okay. Yeah. Thank you.
Yeah. Okay. So these are the singular values of t tensor t. I'm interested on the maximum correlation between two copies of A and B. Okay. And then to do that, I should consider this T operator associated to two copies. And if you do the computation, it's easy to realize that the operator T corresponding to A2B2 is the same as the T tensor with itself. Then the maximum correlation between A2 and B2, two copies, is the same as the second singular value of T tensor T. And I just computed the second singular value of t tensor t. This is S1 of t times S2 of t. But remember, S1 of t was 1. So this is S2 of t. And S2 of t is just the maximum correlation between A and B. That's why we get this tensorization property. If I compute the maximum correlation for two copies of A and B, I get the same number as I computed on the single one. In general, if you have two independent distributions, joint distribution PAB and PA'(B'), where these AB are independent of the prime ones, and I compute the maximum correlation between AA' and BB', I get the maximum of AB, the maximum correlation of AB and the prime ones. The reasoning is exactly the same. I mean, here, instead of t tensor t, I would have like t tensor t prime, and then the second singular values would be like S1 of t times S2 of t prime, and then S2 of t times S1 of t prime. And then the maximum of these two would be the maximum, it would be the second singular value of t tensor t prime, and I would get this one because the S1s are both 1, equal to 1. So I have this general form of tensorization property. Maybe I should stop here again to see if there is any question.
No, nothing.
Okay, great.
Not have content.
Okay, great. Okay. So I told you that data processing can be proved using using just a definition of the maximal correlation, but you can also prove it using this characterization of maximal correlation in terms of the second singular value. Suppose I apply some function on B, okay, and generate Y. Then out of these functions, I have this joint distribution between Y and B, and then I have an associated operator S. It's the same operator that I had before, this conditional expectation. Now here, S goes from a function of B to a function of Y. It's like the same thing. It's just this conditional expectation. Now to compute this maximal correlation between A and Y, I should consider the map that sends a function of A to a function of Y. Okay. Now the point is that this function is the same as sending a function. This map that sends function from A to Y is the same as considering the map that sends function from A to B, composed with a function that maps functions from B to Y. So the concatenation of T and S is the same as this conditional expectation A given B, Y. Okay. So I have this equality. The operator associated with the joint distribution AY is the composition of S and T. And then the second singular value of the product of these two matrices is at most the first singular value of S times the second singular value of T. Again, this inequality is, I mean, you probably have seen this inequality and used it. It's a natural inequality when you consider norms of operators and so on, but just by definition, you can prove this inequality for yourself. Now the point is that S1 is equal to 1, the first singular value. So we have this equality that the second singular value of T is rho AB. So we have this data process. Rho of AY is at most rho of AB. Here I should I should tell you a bit more about this operator S and T and things like that. As I said, you can think of the space of functions as an inner product space. Okay, so let me go back to the previous slides, maybe here. So you can think of the space of functions of A and B, or a space of functions of both of them as an inner product space with this inner product. Okay, then you have some subspaces of this whole space. This space of functions that are functions of A itself, and the space of functions that are only functions of B. Okay, so you have these two subspaces. And then this operator T, if you think about that, is an orthogonal projection from the subspace f of A to the subspace of f of B. In fact, T is a projection. It's an orthogonal projection from f of A to f of B. Okay, it's an orthogonal projection. And this composition here tells me the projection from A to Y is the same as projection from A to B composed with projection from B to Y. So these are already projections on the space of functions. Okay. So let's give some examples. We have the distribution P of lambda that we had before. the corresponding operator T would be a 2 by 2 matrix, because the alphabet size of A is 2. So the space of functions of A would be just R2. If I consider real functions, it would be a 2-dimensional space. Again, f of B would be a 2-dimensional space. So this T matrix would be a 2 by 2 matrix. The second singular value of T would be 1. And the second singular value of T would be the maximum correlation between A and B. Now, if you think about that, the absolute value of the determinant of T would be the multiplication of the singular values. The first singular value is 1, so the absolute value of the determinant is nothing but the second singular value, or the maximum correlation. So you can just write down the matrix T, the matrix associated with T, and then compute its determinant. You would realize that the maximum correlation for a distribution in which A and B are binary would be given by this formula. And then you can use this formula to compute the maximum correlation of this P lambda. It would be just lambda. Or you can do directly do the computations. I mean, the expression for T for this for this choice of distribution, it would be easy to write on what the map T does, and then compute its singular values and so on. So, anyways, the maximum correlation of P lambda is just lambda, and now you can solve this problem that I raised in the beginning of talk for this distribution P lambda and P mu. Suppose lambda is less than mu, and then you have lots of copies of P lambda, the less correlated distribution. The question is that can we generate a single copy of mu? Using these properties of maximal correlation, we can answer this question. If it was possible, then by the data processing, I should have this inequality. The maximum correlation between A and Bn for this choice of lambda should be larger than the maximum correlation between A and B for this. Sorry, this is for the smaller lambda. This is for mu is larger than lambda. By the data processing, I should have this inequality if the non-interactive simulation was possible. And I should have this inequality, but remember, the maximum correlation of P mu is mu, and maximum correlation between An and Bn for this parameter lambda is the same number as I computed for n equal to 1. I get lambda, but lambda is less than mu, so I get a contradiction. It's not possible. Okay. So this is a quantum workshop. So I should talk about the quantum maximal correlation. It's defined in the same way. In the quantum case, instead of a distribution, I have a bipartite density matrix, and the question is that what's the maximum correlation between for this bipartite density matrix? I can define it in the same way. Instead of considering that the expectation, it would be just a trace of my density matrix type something. The something in the classical case, it's a multiplication of two functions. In the quantum case, the functions are replaced by operators, and then the multiplication is replaced by tensor product. And then this is the fact that the expectation of f is 0. This tells me that the expectation of g is 0, and this is the other constraint is the normalization of the variances. So the expectation of like f squared, instead of f squared, I have ff dagger because f and g might be complex. So that's why you should consider the ff dagger instead of f squared and so on. And then you can prove the properties of the quantum maximal correlation by similar kinds of arguments. First of all, you can prove this data processing inequality for any two quantum operations, CPTP maps. If I transform A, B to locally transform A and B to X and Y, then the maximum correlation between X and Y is less than the maximum correlation between A and B. And also I have the tensorization property. Again, the proofs are essentially the same. Instead of functions, you would consider operators, and instead of that T operator, the conditional expectation operator, you can define a similar type of operator using Choi-Yamiakovsky representation, if you're familiar with that, and then prove that this rho is the same as the second cellular value of some super operator. An example is if you take sigma lambda to be a mixture of the maximally mixed state and the maximally entangled state, this is essentially the same, the quantum version of the classical example we had previously. We can show that the maximum correlation of A and B would be lambda. It's the same thing. And then this means that for different values of lambda, you cannot, by local operations, you cannot increase lambda. You cannot distill like larger values of lambda, even if you have lots of copies of the shared state for a smaller lambda. Okay, so I'm done with the definition of maximal correlation. We will see that maximal correlation also appears in the next slide. But I want to next tell you the other measures of correlation with the tensorization property. So I have about 18 minutes, I guess.
Great.
Let me stop here and see if there is any question, and then continue with hypercontractivity ribbon.
So we are not actually inviting questions, so please post your questions on the designated channel on Slack.
Okay. Okay. So I guess there is time for giving some basic definitions of hypercontractivity ribbon, and then we will give more properties of the hypercontractivity ribbon for the second lecture. Okay, so I'll start with the definition of the P-norm. In the previous slide, you saw the definition of the 2-norm. That was the expectation of f squared, and then to the power of 1/2.
May I interrupt with a question?
Sure.
Are F and G unitary matrices that we signed?
Here, no, they are arbitrary operators.
Then the second question asks, can you introduce a bit more about the vector spaces of FA and FB in the classical case? Like, what are their dimensions and bases, and what does the vector in this space look like? Yeah,
sure. So as I said, these are like f of A is the space of functions of A. Okay, so let's say A is binary. It takes values either 0 or 1. So to give you a function of A, I should tell you what f of 0 is and f of 1. So by giving two numbers, two real numbers, I would give you a function of f. Okay. So it's like, so I can think of this function as a two-dimensional vector, where the first coordinate is f of 0 and the second coordinate is f of 1. Okay. So the dimension of f of A is the same as the size of the alpha. Is the same as the alphabet size of A. Okay. And similarly for B. So this map T is a matrix of size A times the size of A times the size of B. Okay, or I should say the other way, the size of B times the size of A. And for the basis, as I just said, for the basis, you can think of like the basis for f of a. You can think of a function that, like if a is binary, for a basis, you can think of a function that for which f of 0 is 1 and f of 1 is 0. And another basis vector is a function that f of 0 is 0 and f of 1 is 1. So it's like this computational basis 1 0 0 1. Okay. Does that answer the question?
Yes, but we are having one more question. Omar is asking, can the maximal quantum correlation also be interpreted as a second singular value?
Yes, it is. So yeah, I skipped this this thing about the quantum case. So in the quantum case, there's an associated super operator corresponding to this joint density matrix. First of all, to define that super operator, you should first somehow normalize sigma, right? This joint thing. The normalization would be in terms of this the marginal states sigma A and sigma B. If I remember correctly, it would be something like this: the sigma A to the power of minus 1/2, and then tensor product with sigma B to the power of minus 1/2, something like that. And then you come up with some normalized, in some sense, a normalized. So the normalization is not the normalization of trace; it's something else. But after doing this kind of normalization, you would come up with some joint operator on A and B. I mean, it's some sigma tilde AB, I should say. And then, if you're familiar with this joint, this Choi-Yamiakovsky representation, if you have a super operator from the space of A to a space of B, you can associate to it an operator which acts on the tensor product of the space of the tensor product of space of A and B. Okay. Now I do the reverse. I have this sigma tilde that is normalization, and then ask what is the what's the super operator whose Choi-Yamiakovsky representation is sigma tilde. And that would be an operator, that would be a map that sends this matrices over the A space to the matrices on the B space. That's a linear map, and then I can talk about this singular values of that map. By similar kind of reasonings in the classical case, we'll see that the first singular value would be 1, and then the second singular value would be just this quantity. I mean, the arguments would be exactly the same. The only difference is that to define that T operator, I should think of this Choi-Yamiakovsky representation.
Thank you very much. There is one more short question. Is the expression of S2 a standard way of representing the second singular value as an optimization problem?
Oh, you mean this one?
I'm guessing
yes, in general, not yet. Yeah, I don't remember the names, but these are famous. Like if you look at this Bahatia's book, this matrix analysis Bahatia's books, you can see this kind of representations for singular values. So yes, these are standard. So the first singular value, which is essentially the norm of this operator, the operator norm of T, comes from the sandwich of T with two vectors and then normalize them. For the second singular value, you can once you have the first the vectors corresponding to the first singular value, then you do the same optimization but restricted to the set of vectors that are orthogonal to the first singular values, and you can repeat this. Like if you want to compute the third singular value, you compute the same optimization, but over vectors that are orthogonal to the first and second vectors, and so on. So these are the standard optimizations and characterization of singular values. Yeah.
Okay, thanks very much. We don't have further questions, and we have 10 minutes until the first break.
Yeah, sure. So I'll give you just some definitions, and then we can go to the break. Okay, so this is the space of functions that we just talked about. This is a vector space, and this is an inner product vector space. Given the inner product is given by this expectation, and this expectation, this inner product in this is a 2 norm. The norm of some vector f, a function f, would be the expectation of f squared to the power of 1/2. And then I can generalize this definition for any p, any number p greater than 1. So the p norm of f would be the expectation of the absolute value of f to the power of p. I take the expectation and then raise the whole thing to the power of 1/p. Okay, so that's a definition of the p norm. If I let p to be equal to 2, I'll get the norm corresponding to the inner product. But for other values of p, it does not necessarily come from an inner product. It's just a norm. It satisfies the triangle inequality, so I can think of it as a norm or a distance. And then I have this important Holder duality. Given p, I can associate to it a number p prime given by this equation. And then I have this characterization of this p norm. The p norm of f is the maximum of the absolute value of the inner product between f and g, where the maximization over all is over all choices of g, whose p prime norm, this Holder dual here I have, and the p prime norm is at most small. Okay. And the proof of this is not really hard. You can just take the derivative. I mean, fix f, and then to compute this maximum, just take the derivative. You'll find what the optimal g is, and then this norm pops up as the optimal objective value. In other words, this inequality tells me that this optimization characterization of a norm of p norm of f tells me that the expectation of fg, or the inner product between f and g, is at most the norm of g, the p prime norm of g times the p norm of f. Okay. And this is really a generalization of the Cauchy-Schwarz inequality. If I let p equal to 2, then p prime would be 2. And then these norms, both of them are the 2 norms, or the usual norms that we have in the for vector spaces. And then this inequality tells me that the inner product between f and g is norm of f times norm of g. If I change p, I get other inequalities, which are called the Holder's inequality or Holder's duality sometimes, and these are generalizations of Cauchy-Schwarz. Maybe to get some intuition, I just told you that if p is equal to 2, p prime would be 2. Okay. If p is equal to 1, then p prime would be infinity, and the other way around. If of course, if p is infinity, so in this definition also you can define it as p goes to infinity, like that. Like in fact, the infinity norm of f is the maximum of the coordinates of f. It's the maximum of f of 0, f of 1, and so on. The maximum of the absolute value of f of 0, f of 1, and so on. So if p is equal to infinity, p prime would be 1. So these are like the dual of each other. These spaces with different norms. When the norms are related by this equation, then they are dual of each other because of this characterization. Okay, and then even more, we can generalize this inequality here. We can say that if P, Q, and R are three numbers greater than 1, so that we have this equation. This is, as you see, is a generalization of this one. When you pick R to be 1, you get this equation here. In general, if you have this equality, then we have the R norm of Fg is at most the P norm of F times the Q norm of G. The point is that if R is equal to 1, then the one norm is essentially the expectation of the absolute value. So as you see, this is a generalization of this one, but given this equality, proving this is not hard. It's by just replacing F with like F to the power of R, and G with the G to the power of R, putting this in this equality and then inequality, and then you realize that this inequality also holds. What can we learn about this one? Suppose that G is the constant function. Okay, then F times G would be just F, and then the Q norm of G would be just 1, because here, if like my function is constant equal to 1. 1 to the power of P is 1. If I take the expectation, again, I get 1, and then raised to the power of 1 over P, I get 1. So the norm of this constant function 1 would be just 1. So I get 1 here. So what I get is that the R norm of F is at most the P norm of F. Okay, and because of this equality, here, I know that R is less than P, because I know that P and Q, these are greater than 1. In particular, they are positive. So if I ignore P here, and in fact, think of this 1 over P as a positive number, I realize that R is less than P. So that's why for letting G, for this special case where G is a constant function, I realize that the R norm of F is less than the P norm of F, which essentially means that this function that maps P to the P norm of F for any function F is a non-decreasing map. As I increase P, I would get larger and larger numbers. Okay. Okay, I guess I'm done with the time. I guess it was good to introduce these norms, and then I can go to the definition of hypercontractivity.
I wonder if you can answer a short question.
Sure, of course.
It has to do with the structure of the optimal F and G matrices in the example that you showed. Could you please shortly comment in the next slide, I guess?
Okay, so yes, that's a good question. So yeah, well, it's easy to guess because the vectors F and G corresponding to the first singular values are constant vectors. Like these are like 1, 1 vectors, like vectors whose coordinates, both of them are 1. Okay, and then you want to find the optimal functions. Let me go back to this previous slide. Yeah, here. So to find the optimal F, in particular, F should be a function whose expected that is orthogonal to 1. The function that is orthogonal to 1, there's a single function because it's a 2-dimensional vectors. One of them is this 1, 1 vector. The other one would be there's a single vector that is orthogonal to that one, and that single vector is just 1 minus 1, and that's normalized. The expectation of F squared would be. The expectation of F would be 0 because it's 1 minus 1, and you're computing the expectation with respect to uniform distribution. Here, the distribution of A is uniform. Distribution of B is also uniform. So these expectations would be with respect to uniform distribution. So 1 minus 1 for both F and G are the optimal functions. Okay, and they are normalized. Their variance is also 1. Because F squared is 1 and G squared is 1.
All right, thanks very much. I think we can start our break. So we will continue in 30 minutes from 12.
Okay.
Okay, all right. We will continue with the second half of the tutorial. Please go ahead. I think you will need to share your screen.
Yeah, sure. Do you have the screen now?
Yes, great.
Okay. So let's
okay, all right. We will continue with the second half of the.
Okay. Okay, so we want to talk about another pressure correlation with the tensorization property, and that's a hypercontractivity ribbon. I told you about this definition of the norms. The definition for any p greater than 1 is given by this quantity. We have the Holder inequality, where p and p prime are related with this equation here. And then using the Holder inequality and some sort of scaling, we find that this map that for any function f, the map that sends p to the p norm of f is a non-decreasing map. Okay. Now, remember this definition of this conditional operator T, which, as before, we can think of it as a projection from the space of functions of A to expression of functions of B. The P to Q norm of this operator is defined in this way. So this is the maximum Q norm of T of F. Okay, over all functions of T with whose P norm is at most 1. Okay, so you are considering the image of F, the Q norm of the image of F. Remember that we have P to Q norm, so Q sits in the image and P sits in the pure image. So we compute the TF, the image of F under this map, the Q norm of T, the image, and then comparing to the norm of the F itself. And then ask what's the best number that I can put here? What's the best scaling number that I can put here in such a way that the norm of the image is at most that scaling of the norm of F. So in the space of inputs, I put the P norm, and the space of output, I put the Q norm, and then try to compare them with the best constant that I can put there. Okay. So that's the definition of the P to Q norm. Now, now using this duality, the Holder duality, and we realize that this norm is the best number that in such a way that the expectation of F times T of the expectation of G times T of F is at most that number, the P norm of F times the Q prime norm of G. So why do I have this? Because remember, if I want to compute the Q norm of T of F, I should maximize over all G, the expectation of G times this guy, over all choice of the G whose Q prime norm, the Holder conjugative Q, is at most 1. So if you just use this condition here, or this duality here, and use it for the Q norm of T of F, you would realize that the P to Q norm of T is the best constant that I can put here in such a way that this inequality always holds. Okay, it's just this inequality and then apply the Holder duality and this quantity here. You would come up with a G. We want to optimize over a G whose Q norm is some bounded, or you can scale both sides by the norm of G. And we just saw that in the previous lecture that the expectation of G times T of F for this choice of F is nothing but the expectation of the multiplication of F and G. Okay, so the P to Q norm of T is the best constant such that the expectation of Fg is at most that constant times the P norm of F times the Q prime norm of G. Okay. On the other hand, we know that by Holder's inequality that the expectation of Fg is at most the P norm of F times P prime norm of G. This means that the P to P norm of T is 1, at most 1. Okay, so just compare this inequality with this one. Okay, let Q to be the same as P. Okay, then the Holder inequality tells me that the expectation of Fg, which is the same as the expectation of T times T, G times T of F, is at most the P norm of F times the P prime norm of G. So this means that the P to P norm is at most 1. Okay, or in other words, by the definition of the P to P norm, it means that if I equip both the input and output space of T by the P norm, then T is a contraction. If I start with a vector F with norm, with a given norm, the norm of the image of F with the same norm, with the same P norm, would be smaller. So it contracts this space. So that's why this is a contractivity inequality. It says that the image of some vector, the length of the image of the vector, or I should say the norm of the image of a vector is at most the norm of the starting vector. And you can prove this inequality even using the convexity of the function x to the p, the function that sends x to the x to the power of p. So you can either use this Holder inequality or directly use this convexity property. It's easy to derive this inequality. So now I'm interested in inequalities that are stronger than this one. Okay. I'm not interested on P to P because it always holds for any operator T of this form, for any conditional expectation operator. I'm interested in stronger types of inequalities. I'm interested in inequalities, the upper bound 1 on the P to Q norm, where Q is greater than P. Why this would be a stronger inequality? Because in that case, here I would have Q, okay, and then the Q norm of F, because Q is greater than P, would be smaller than the P norm. So that's why for this choice of parameters, P greater than Q greater than P, an inequality of this form would be stronger than this one. Here I'm using this property of, I'm using this property of the P norms, that the P to the P norm of F as a function of P is a non-decreasing function. That's why inequalities of this form, when Q is greater than P, would be stronger inequalities than this one. And because they are stronger than this contractivity inequalities, they are called hypercontractivity inequalities. Okay. Okay. Just because this is an important definition, let me review what I just told you. So we have this T operator, this conditional expectation, and we are interested to the in P to the Q norm of this operator. And this is the best number that I can put here to satisfy this inequality. Using this this Holder inequality or the convexity of the x to the p function, we realize that the P to the P norm is at most 1. In fact, it's equal to 1 because we can always take f to be the constant function, for which well, we realize that this is greater than equal to 1, and then this is in fact equal to 1. Anyway, so for P equal to Q, we have this contractivity inequality. And then using this property of the monotonicity of this P norm, we are interested in inequalities that are stronger. We are interested in inequalities of this form, P to Q, where Q is greater than P. And because these are stronger than the contractivity inequality, we call them hypercontractivity inequalities. And then this comes the definition of the hypercontractive ribbon. This is for given a joint distribution between A and B, I have this conditional operator, conditional expectation operator T, and then I put in a set R of AB, R stands for ribbon, all pairs Q and P, where Q is greater than P, both of them are greater than 1, in such a way that the P to Q norm of T is at most 1. Okay, this is a this R of AB. This is a subset of the two-dimensional plane. This is the Q axis. This is the P axis. I assume that P and Q are greater than 1. That's why I have this this lines here that pass through this point 1 and 1 on both axes. And then I'm interested on sets that Q is greater than P because other values are trivially hold, so I exclude them. And then I will come up with a set, and that set is going to be my hypercontractive ribbon. So this is a ribbon because usually the shape of this set would be of this form. That's called a ribbon, and it's called hypercontractivity because it's related to this hypercontractivity inequalities. Okay. So this is an invariant which depends on my starting distribution P of A. Okay. And I guess I told you about this in the previous slide. If QP is in the hypercontractive ribbon, this means that this norm is at most 1, and then use the duality, you would realize that this is the same as this inequality to be satisfied for all functions f and g. Okay, so here, because I'm using Holder duality instead of q, I have q prime. So here you should notice that this hypercontractive ribbon is not symmetric because you would realize this asymmetry here. Here I have QP to the hypercontractive ribbon if the expectation of FG is at most the P norm of F times the Q prime norm of G. So it's asymmetric, but we should keep in mind that like A is the input space and B is the output space, and, or you could change the definition and take this one as a definition of the ribbon. Okay. This hypercontractive ribbon is going to be a measure of correlation in some sense for us. So let's assume that A and B are independent and see what's the hypercontractive ribbon is going to be. So if A and B are independent, meaning that their joint distribution is a product, then the hypercontractive ribbon would be this whole set here, this whole all pairs in this part of the plane. Why is it the case? Because as before, because it's a product distribution, the expectation of FG would be expectation of F times expectation of G. And remember, the expectation of F, because of one reasoning is the Holder inequality. You can there are other reasoning for that as well. So the expectation of F is at most the P norm of F, because P is greater than 1, and this is essentially the 1 norm, right? And similarly, the Q prime norm of G is at most is an upper bound on expectation of G. So the product is an upper bound on the product, and using this dual characterization of the hypercontractive ribbon, we realize that the QP for any Q and P belongs to the hypercontractive ribbon. So the hypercontractive ribbon, when P and Q, sorry, for when A and B are independent, would be the largest possible region. So it's hypercontractive ribbon is a subset of this region here, this triangle shape here, and for in the independent case, it would be exactly this largest possible set. Okay. Let me prove the data processing. It's similar to the proof of the data processing. Well, I should say the second proof of the data processing inequality for this maximal correlation. If y is a function of b, then the hyperconjugative ribbon between a and b is a subset of the hyperconjugative between a and y. So by local processing, the hyperconjugative gets larger and larger. Okay, and it makes sense because and in the previous slide we saw that the hyperconjugative ribbon for the independent case is the largest possible set, and this says that this monotonicity holds in the direction that the hyperconjugative ribbon expands. If you locally manipulate your data, then the correlation, when measured in terms of the hyperconjugative ribbon, gets larger. It expands. Okay, so it gets more. So the largest hyperconjugative ribbon, which means less correlation, and then that's captured by this line here. And how we can prove it is easy. Again, I'm interested in the map that sends a to y, this conditional expectation, or this projection that sends functions of a to function of y. And I can do it in two steps. I can go first from a to b, and then using this function go to from b go to y. So what I mean is that the operator, this conditional expectation operator from a to y, is equal to the composition of the t, the operator from a to b, with s, the operator, the projection from b to y. So we had this expression before, if you remember. And then suppose that I have some pair here, some pair QP here. This means that this norm here, then this means that this norm here is at most 1, right? That's by definition of PQ being in this set here. And now using this this assumption, I want to prove some upper bound in the unconditional expectation from A to Y, which is this composition of these two maps. And what's this one? Well, this is some standard computations when you manipulate these kind of norms. The P to Q norm is at most the P to Q norm of T times the Q to Q norm of S. So think of like 3 spaces. This is my starting space, this middle space, and this last space. The question is how much the space expands, the norm expands when I move from this space to that one. This inequality tells me that the amount of expansion is at most the amount of expansion when I go from this space to this one, multiplied by going from the middle space to the last one. That's the meaning of this inequality here. And then remember, this Q to Q norm is always at most 1. This was a consequence of this Holder inequality. And then I have this inequality. Well, in fact, I have this equality here because I told you that this is exactly equal to 1, not just less than or equal to 1. So we have this equality. So then it means that I guess you faced a problem with the voice. Do you have the voice now? Because I guess something went wrong with my mic.
I think everything is fine now.
It's fine. Okay, great. Okay. Okay, anyways, the whole point is that the map from A to Y is a composition, and then we can bound this P to Q norm with the multiplication of the individual, the norm of individual maps, and then one of them would be equal to 1, so we have this inequality. If QP is inside this hyperconjugative ribbon, This means that this guy is at most 1. As a consequence, this one is at most 1, which means that QP belongs to the hypercontractivity of A to AY. Or in general, you can generalize it. It's essentially the same kind of argument. And if you have this chain rule, in general, the hypercontractivity of the AB is inside X and Y. So if Alice and Bob both locally manipulate their whatever they have, and the resulting hypercontractivity ribbon would be a subset of the starting hypercontractivity ribbon. Okay, so this is the data processing, and exactly because of the data processing, I think of this hypercontractivity ribbon as a measure of correlation. Well, it's not just a single number, but a set, but I think it's monotone under this inclusion. Then I can think of it as a measure of correlation. I want this measure of correlation to satisfy the tensorization property. Let's verify that. We saw previously that the operator that maps the AN part, the AN subspace to the BN subspace, comes from the tensor product of NT with itself, the n-fold tensor product. And now the point is that the n-fold tensor product of T with itself, if I compute the P to Q norm, it's nothing but, sorry, it should be P. This guy here should be P. It's a typo. It's equal to the P to Q norm of T to the power of N. So the point is that this operator norm is multiplicative. That's why this thing with tensor product is translate to a power on the other side. Which means that if this guy is at most 1, then this guy is at most 1, right? So that's why the hypercontractivity ribbon between AN and BN is the same as the hypercontractivity ribbon between A and B, and that's my tensorization property. This comes exactly because of this multiplicativity property of the operator norm. More generally, if I have two independent distribution, P and AB, and then the prime one, then the hypercontractivity ribbon between AA prime and BB prime is the intersection of the two hypercontractivity ribbons. Okay. The argument is the same as before. If I have like T tensor T prime, or when I compute its norm, it would be the same as the norm of T times the norm of T prime. And then if both of them are less than 1, then I get a number that is at most 1, and then that's why we have equality. So we have this data processing of hypercontractivity ribbon. That's a measure of correlation. We have this tensorization property. So it's a good measure of correlation to be applied on the problems that we started. Okay. Let me give you an example. Usually, computing this hypercontractivity ribbon is a hard problem. But if you consider these distributions that is repeated many times in this talk, I told you before that computing the T operator is easy. It's the T lambda of F is, it replaces F with a convex combination of F and the constant function expectation of F, where the parameter is just lambda. And then this is a famous inequality. Sometimes it's just called the hypercontractivity inequality. Sometimes it's called the Bonomi-Beckner inequality, but maybe the full name is Bonomi-Nelson-Gross-Beckner inequality. So it says that this exactly characterizes the hypercontractivity ribbon. It says that the P to Q norm is at least 1, if and only if this inequality is satisfied. It essentially says that the hypercontractivity ribbon is a region here, the blue shaped one, where the slope of this line that passes through this the 1, 1 point is lambda squared. The lambda is the parameter that we have here. Okay. And then, as you see, if I increase lambda, then I get a smaller hypercontractivity ribbon. Then I can, so it means that I can compare this distribution for different values of lambda with each other, and realize that when lambda gets larger, then the correlation in P of lambda becomes, I get more correlation. Okay, what else I can learn about this theorem? Remember, lambda, this parameter lambda is equal to the maximal correlation of P lambda, right? The maximal correlation that we studied in the previous lecture for this distribution is equal to lambda. So probably the hyperconjugative ribbon and maximal correlation are somehow related. And that's given by this theorem. If QP, this pair, belongs to the hyperconjugative ribbon, then this inequality holds where rho is the same maximal correlation that we had before. What's the proof? I would like to sketch the proof for you. So in the definition of rho, we are starting with two functions. Here I'm calling them f prime and g prime, which have zero expectation and unit variance. Okay. Now I'm introducing two new functions, f and g, which are like perturbations. You can think of them as perturbations of the constant function. So it's 1 plus some epsilon, epsilon some small constant, and alpha is some constant that which we determined during the proof times f prime. So it's so because epsilon is a small constant, it's a perturbation of the constant function. It's the one function, and the same for g. But the scaling for g would be alpha minus 1 instead of alpha. And then because if I start with QP, remember that is equivalent to this inequality. That's from the assumption that the QP belongs to the hyperconjugative ribbon. So now I want to expand both sides of this inequality as a function of epsilon. Okay. The largest term, of course, would be 1, right? Because the expectation of fg, if I take epsilon to be 0, would be just expectation of the one function, which is 1. And the same here, the norm of the one function would be 1. And so that's why the leading terms, when I expand it as functions of epsilon, would be 1. And the second term, which is like epsilon times something, that would be 0 because of this thing. That's a simple computation. I don't want to bore you with that. So the interesting term would be the second term, the coefficient of epsilon squared. For this side, it's easy. It comes from the alpha f prime, the expectation of alpha f prime times alpha inverse g prime, which is the expectation of f prime g prime. And you can do some calculations. I mean, you should compute the second derivative of this norm function in terms of as a function of epsilon. You would realize that we have this equality, which is like alpha squared times something plus alpha to the power of minus 2 times something. Then if you choose alpha appropriately, you would realize that this is equal to the multiplication of these two. Well, the square of the multiplication of these two. Well, in some sense, you're replacing an average with a geometric average, geometric mean. So you come up with this one, and then by using using the fact that these are normalized, this normalization here, and replacing q prime, rewriting q prime in terms of q, you would come up with this inequality, and then comparing the two sides of the inequality, you would realize that the expectation of f prime g prime not most this one. And the expectation of f prime and g prime, if you maximize over f prime and g prime, that would be the maximal correlation. And that's why the maximal correlation is at most the square root of p minus 1 over q minus 1. Okay.
May I interrupt with a question?
Sure.
The question asks, when the multiplication of the norms is less than 1, how can we conclude each is less than 1? So in other words, why the joint ribbon is included in the intersection?
Yeah, yeah, I skipped over that. Well, the point is that, as I said, maybe I told you about that somewhere. And yeah, maybe I told you about that here. So the point is that the P to Q norm is always greater than or equal to 1. This is none. Why is it the case? Because you can take f to be the constant function. Okay, when f is a constant function, let's say 1, the 1 function. The conditional expectation is just 1, right? So the t of 1 is 1. And any norm of the constant 1 function is 1. So here I put f to be 1, and then t of f would be 1, and then the norm would be 1. So it means that this norm is at least 1. Then in fact, this contractivity and hypercontractivity asks whether the norm is exactly equal to 1. So I define the hypercontractive ribbon. I ask when this is less than or equal to 1. I could have asked whether this is equal to 1. These are the same questions.
Okay, thank you.
Okay, yeah, that's why we have this equality. Okay. Okay, now I have this theorem. So if I think of this hypercontractivity inequality, which is translates to this inequality here, and then consider this inequality for functions f and g, which are almost constant functions, then I realize then I discover the maximal correlation. Well, the second theorem is a dual representation for the hypercontractive ribbon. Remember, I told you that mutual information is an additive measure of correlation, but surprisingly, you can interpret or can express the hypercontractive ribbon in terms of mutual information. So it says that this is a theorem, so that the QP belongs to the hypercontractive ribbon if and only if for any extension PUAB, but by extension I mean any distribution over U, A, and B whose marginal over A and B is the starting distribution. So that's what do I mean by an extension. So to this condition, the second condition is that for any such extension, I should have the mutual information between U and AB is an upper bound on 1 over P mutual information between U and A plus 1 over Q prime mutual information between U and B. Which is a surprise because when you first look at it, mutual information is additive, but with some inequality, it characterizes the hyperconjugative ribbon, which is a measure of correlation with the tensorization property. Now, remember that if 1 over P plus 1 over Q prime is less than 1, then the inequality that P to Q norm was always less than 1. And you can easily see that from this inequality here. If 1 over P plus 1 over Q prime is at most 1, then by data processing, I can upper bound 1 over the mutual information between U and AB by 1 over P. Well, I should put it in this way. So by data processing inequality, the mutual information between U and AB is at most the mutual information between U and A. At the same time, the mutual information between U and AB is an upper bound on U and B. And now the point is that 1 over P plus 1 over Q prime is at most 1. If I have this condition, then putting like the previous two inequalities and takes an average, we get this one. So previously I had this conclusion using this Holder inequality or the convexity of this function x to the p. But here, using this data processing inequality for mutual information, I have this inequality, which is easy to understand. The other thing is that if you take this one as the definition of the hyperconjugative ribbon, then we can prove data processing and tensorization of the hyperconjugative ribbon. And the proof would be like using the standard manipulations of mutual information, using chain rule and then data processing, things like that. So I could have started with this definition and then prove these properties of the hyperconjugative ribbon. The other thing is that this definition suggests to generalize the definition of the hyperconjugative ribbon, not just for for a pair of random variables, but for a tuple of random variables. If I have n numbers, if I have n random variables a1 to an, then I can define this hyperconjugative ribbon to be the set of tuples p1 to pn, such that this inequality is satisfied. As you see, this is the generalization of this one. And you can show that the same theorem it holds for arbitrary n as well. If I have this inequality, it's the same as this inequality for any functions f1 to fn, which is a generalization of this hypercontractivity. Okay, let me tell you a little bit about the proof of this theorem, because it's really interesting. I'm actually tell you the proof in one direction. Okay, so I'm assuming that QP belongs to the hyperconjugative ribbon. I want to prove this. Okay, by the tensorization property, if QP belongs to the hyperconjugative ribbon, it belongs to the hyperconjugative ribbon of AN BN, to the n-fold version. Okay, this means that if I have a function of AN, so it's a function of so the input of this function would be like A1, A2 to AN, little A1, little A2, and so on. And a function of Bn, then I have this inequality. That's a result of the assumption and the tensorization property. Okay. Now, now the idea is to take f and g to be the characteristic functions of some sets. By characteristic function, I mean a function which is 1 on some set and then 0 elsewhere. Okay. And then what's that set? That's going to be some typical set. Okay. So I'm considering AN. So AN, each coordinate of this set of a tuple in AN would be an element of A, like A1, as I said, A1, A2, and so on. And then I'm considering the frequency of like each element of A inside this sequence A1 to AN. And a typical set is a set of all tuples for which this frequency is a constant or almost constant. Okay, and then what happens here? For example, here, if you compute the norm of P, it would be like the expectation of f to the power of P. F is a 0-1 function, so f to the power of P is just f itself. And the expectation of the characteristic function is the probability of the corresponding set. So what appears is the probability of some typical set. And people familiar with this theory of the typical set will realize that the probability of a typical set is related to the relative entropy or KL divergence between that frequency pattern and the original distribution that they started. So that's how this norm is related to KL divergence, relative entropy, and then to mutual information. Okay, so I'm not going through the details, the proofs in details, but the whole idea that you can keep in mind is that to prove this theorem, I can think of functions that are, I first go to the tensorized version, to the n-fold version, and then think of functions that are characteristic functions, and then take typical sets. Okay. Yeah, I wanted to tell you something else about this theorem, is that you can prove this theorem as a duality. So in some sense, the fact that, I mean, if you think of computing this hyperquantitative ribbon, it's a convex problem, if you think about that. I mean, if you think of it as an optimization problem over the problem of computing the norm of an operator T, you can think of it as a convex optimization problem and then take its dual. That would be the dual representation. So these are really the dual representation of each other when you think of optimization problems. Okay. Let's move on. We can learn even more about the hypercontractivity ribbon using this representation. Remember, I told you that mutual information is an additive
continue, may I start with a question? Sure. I'm not sure if I understand the question, so I just read the question. How come in the generalization we don't use the dual of any of the PI? Meaning that how does it generalize the characterization?
Yeah, well, the point is that when we have two, in the bipartite case, we have A and B, so we can pick one of them as the input space and the other one for the output. But here, for the n-partite case, it's, well, it's hard to tell which one is input and which one is output and so on. So that's why you don't see any dual version here. So as I said, I could, in the definition of the hypercontractivity ribbon, instead of taking pairs Q and P, I could have taken pairs Q prime and P, so that I get this symmetry. So that's just a matter of notation and how you define the hypercontractivity ribbon. In fact, in the original definition of the hypercontractivity ribbon in this paper, well, they don't call it hypercontractivity ribbon, but in the original definition, they take this guy here, this one here that I. But if you look at the papers that, for example, this paper that we have with Amin, we take this one as it. I mean, we take Q prime as and P to be these pairs as consist of hypercontractivity ribbon. So that's just a matter of definition and taking the notation. That's not really deep in there.
Thanks very much.
Okay, as I told you, one side of this theorem we have a tensorization property, the other side we have mutual information with the additivity property. So probably this duality of additivity and tensorization is something deeper, and it is in fact. Let's define J of AB to be the set of all triples consisting of all this mutual information of UAB, UA, and UB, all the terms that appear in this theory. And I'm taking all of these triples over the choice of these extensions PUAB. Okay. Then you can easily show that this set is a convex set. And in fact, it's a set of this form. Well, this is a two-dimensional thing, but this is a three-dimensional subset, but I guess you get the idea. This J of AB is a convex set, and this is also additive. I mean, if I take A prime, B prime to be independent of AB, and then compute this set for AA prime versus BP prime, I realize that this is equal to the summation of these two sets, where by summation, I mean the point-wise summation. I get some point here and then some point here, sum them up, and then take all of the sums. That's what I mean by the summation. So this J set has an additivity property. And you can prove this additivity property using the standard compute manipulations of mutual information, like chain rule and things like that. So it's not obvious that this is additive. This equation is not obvious, yet the proof is not hard. It's easy. Now, the point of this theorem is that the hyperconjugative ribbon, the R set, is the dual of the J set. Where the dual, I mean, is essentially the set of hyperplanes or lines in this picture that split a space, and then the J set, it belongs to one side of the line. So this inequality essentially says that describes one of these hyperplanes. Okay, and it says that the R set is a dual of the J set. If I start with the point here, and then I'm interested in inequalities of this form, and inequalities of this form are the hyperplanes, which describe a point in the dual picture. So that's why this J set is a dual of the R set. Okay. So as I said, this duality of additivity and tensorization is even more than that. In fact, you can do it even more generally. You can start with some arbitrary source coding problem. Okay. Let's say the Gray-Weiner problem, if you know that, or something else. So choose your source coding problem of your interest, and then compute its rate region. Okay. And then take the dual of that region. Okay. And that dual would satisfy the tensorization property. The point is that the rate region, by the very fact that it's a rate region, has the additivity property. I mean this one. Any rate region, by definition, no matter what source coding problem you consider, satisfies the additivity problem. And then you take the dual, you automatically get a problem, a set with the tensorization property. The logic would be exactly the same as the logic we had here. The other point is that if I start with a source coding problem, usually for such problems, the rate region satisfy a monotonicity property. Okay, so that's why if I consider the dual also satisfies some monotonicity property. I mean the data processing inequality. Okay. So in some sense, the additivity the duality of additivity and tensorization is even deeper than that. You can start with any source coding problem, take its dual, and then the dual would satisfy the tensorization property. And it's a measure of correlation if the tensorization if the starting source coding problem has some nice property. For example, if you know what the source coding problem of Gray and Weiner is, this region that I defined here is related to that Gray-Weiner problem. And then this means that the hyperconjugative ribbon, this theorem says that the hyperconjugative ribbon is the dual of the rate region of the Gray-Weiner problem. Okay. And you can look at this. You can look at this paper for more examples of this. Okay. The next thing that I want to talk about is the strong data processing inequalities. So remember, I have this data processing inequality for mutual information. If I have this Markov chain condition, meaning that like U is a function of A, then the mutual, yeah, you can think of it U as a function of A or a stochastic function of A, and then the mutual information between U and A is greater than the mutual information between U and B. So because like A is closer to U, so the mutual information between these two is more than the mutual information between U and B. So this is something known that's I told you about it in the beginning of the first lecture. But now I'm interested on a strong data processing inequalities, meaning that I'm looking for some constant eta that are strictly less than 1, such that if I shrink the mutual information between U and A by this constant eta, I still have an upper bound on U of and between U and B. Okay. So by definition, eta, which here the best eta, which here I denoted by S star, is the supremum of the ratio of UB over U of A. So that would be the best eta that I can put here for which this inequality holds. And I'm taking the supremum or maximum over all choice of U for which we have this Markov chain condition. Now, the interesting fact is that this strong data processing constant, this S star, can be characterized in terms of the hyperconjugative ribbon. It's equal to the infimum of Q prime over P prime, where Q prime and P prime are the Holder conjugates, over all choices of Q and P inside the hyperconjugative ribbon. Okay. Well, one direction of this theorem is easy if you use this characterization and think about that. It's one direction is easy, the other direction is not obvious, but it holds. And you can see that this S star satisfies the tensorization property. Why? Because it can be characterized in terms of the hyperconjugative ribbon, and hyperconjugative ribbon satisfies the tensorization property. So we have this. The other interesting thing is that it's kind of related to this idea of this S star is related to in the idea of this duality of rate regions and measures of correlation with the tensorization property. You can characterize S star as the initial efficiency of the problem of common randomness generation with one-way communication. Okay, so let me tell you what the problem is. So suppose I have this, it's the same as this problem of a non-interactive distribution simulation. So I have this input distribution P A and B, and I want to convert it with local operations to shared randomness, perfect shared randomness. And the question is that what's the rate at which I can do that? Okay. In general, I cannot do that exactly because of the reason I told you, because of this. Usually it's impossible using like the characterization of using like the properties of hyperconjugative ribbon or the maximal correlation and so on. So I want to add a little bit of communication, one-way communication from Ali Subah, and see given like a rate for communication, what's the rate at which you can generate common shared randomness. Okay. The rate region of this problem would be a set of pairs, right? A rate for communication and a rate for the shared randomness, for the generation of shared randomness. As I said, if I let the rate of the rate of communication to be 0, then the amount of shared randomness would also be 0. So I like in the space I have like a curve. Like if you give me this amount of communication, I get this amount of shared randomness and so on. But at point 0, when the amount of one-way communication is 0, I get 0 rate of producing shared randomness. Now, by initial efficiency, I mean the derivative of this curve at point 0. In fact, I'm asking, what if I allow an epsilon amount of one-way communication? What would be the rate at which I can generate common randomness? That thing would be S star. And that comes from this theorem, essentially. The point is that this problem of common shared randomness generation with one-way communication can be characterized in terms of mutual informations with some auxiliary random variable U like this. And then that initial efficiency or that derivative would be essentially the supremum, and that's why we get this S star. So this example of S star is an example of the scenario that I told you about. You can start with some source coding problem and then take the dual, and then the dual would satisfy the tensorization property as monotonicity property. If you take that problem to be this problem of common shared randomness with one-way communication, the associated quantity that you get is this S star.
There's a question. So can the duality between additivity and tensorization be generalized to something in between? Like there is some other?
I don't know. Yeah, that's a good question, I think, yeah. But I don't know. Yeah.
Like we have the one norm and also we have infinity norm, which are extended to P norm and Q norm, etc.
Well, so the duality that I consider here is not the duality between, I mean, it's not Holder duality. It's the duality in terms of a region set here, which could be any set, and then these hyperplanes. The duality that I consider here has nothing to do with the Holder duality. But yeah, maybe we can have some other measures of correlation which are not additive nor satisfy the tensorization property, and then think of what happens to their dual in this sense. I don't have an example of a measure of correlation with this property. Yeah, maybe the quantum ones would might be good examples of this form. Yeah, I'll get to the quantum ones the following, but I don't have any explicit examples. Yeah.
Okay, thank you.
Okay, so this is a strong data processing inequality. Yeah, some remarks. As I said, computing this hyperconjugative ribbon is in general is a hard problem. I mean, an exact characterization of this set is a hard problem in general. And so a useful tool for computing these things is log level of inequalities. I don't want to tell you what the log level of inequality is, but in particular, that Bonamy-Beckner inequality that I gave you as an example can be proved using such a logarithmic level of inequality. The other thing that I actually mentioned before, we can generalize this definition of hypercontractivity ribbon to the multipartite case. The other thing is that we can also consider the reverse hypercontractivity inequalities, in which case we are dealing with numbers P and Q, which are less than 1. Okay. Again, I don't want to tell you the details, but the same kind of arguments happens. The point is that our starting point for when we were dealing with P and Q greater than 1 was the Holder inequality and Holder duality. The point is that the same kind of inequality, the reverse Holder inequality, holds for P and Q less than 1. In which case, then we can start talking about the theory of reverse hyperconjugative ribbons, and you can see that some in this paper you can learn about this kind of inequalities. The other thing is that given a function phi, so phi here is going to a function, I can define some phi entropy. So for given a function f, the phi entropy of f is the expectation of phi of f minus the phi of expectation of f. For example, if I take phi to be the square function, it would be the variance. So I can think of a variance as an entropy. Or if I take phi to be x log x, we essentially get the usual entropy, or to be more precise, we get the relative entropy. So this phi entropy would be an entropy or relative entropy. And then using the characterization of the hyperconjugative ribbon in terms of mutual information, you can generalize that characterization, because that characterization in terms of some entropy function, and then you can take that entropy function, replace it by this phi entropy function, and then define a phi ribbon instead of the hyperconjugative ribbon. This function f, this function phi should satisfy some property. The first property, which you can guess from this expression here, it should be convex, but it should satisfy something more. In fact, if you take phi to be x to the alpha, where alpha is between 1 and 2, you get a ribbon, a phi ribbon for any of these functions. And if you normalize it correctly and then take the limit of alpha going to 1, you get this x log x function. It's the same kind of normalization when we talk about the Rayleigh entropy and then the usual entropy. And then we have a conjecture that these ribbons really, for different values of alpha, interpolate when we move alpha from 1 to 2. For example, we saw that if alpha is equal to 2, we get this, this function x squared, and we essentially get the maximal correlation. So the maximal correlation is essentially the same as phi ribbon when my function phi is x squared. And we saw a relation between the hyperconjugative ribbon, which corresponds to the x log x function, and the maximal correlation. This conjecture says that such a relation is even deeper. When we increase alpha, we get a monotone set of ribbons that are monotone under inclusion. Okay, and you can see, look at for details of this this result. You can look at this paper, I guess. Yeah. And finally, you can define this hypercontractivity ribbon in the quantum case. I told you in the definition of the quantum maximal correlation that we can define that T operator in the quantum case as well, using this Choi-Yamiakovsky representation. And then we can ask about the P to Q norm of that operator, okay? And then define this quantum hypercontractivity ribbon. Proof of the monotonicity property, the data processing inequality for that quantum hyperconjugative ribbon is, well, it's not easy. I should say that the proof is the same as the proof of the monotonicity of the quantum Rayleigh entropy. It's the same nature. You can see the details in this paper. But you can prove the monotonicity property, this data processing inequality. But the tensorization is a hard problem. In fact, the tensorization probably doesn't hold in the quantum case. I don't have. Probably we have an explicit example, but the point is that unlike the operator norm, the super operator norm is not multiplicative. Remember that we proved the tensorization property of the hypercontractivity ribbon in the classical case using the multiplicativity of the operator norm. But in the quantum case, instead of operator norm, we have super operator norm, but the super operator norm, unfortunately, is not multiplicative. That's why the tensorization is not it's not correct in the quantum case, but you can do other things. In some special cases, we do have tensorization, so we can use it, and there are also other ways of moving around this tensorization problem. And you can look at this paper for more details about the quantum hyperconjugative. I guess it's a good time for maybe a break, actually. How much time do I have? Yeah, maybe it's a good time for a break and also taking some questions. Maybe like a 5-minute break would be a good idea.
Yes, sure.
In the meantime, I'm available for questions.
The questions are invited in the Slack channel. So.
Okay. Okay. So let's stick to this break plan, and then I will start with in like 5 minutes. Is that okay, Farsi?
Okay, sure.
Sure. Okay, so let's.
Thank you. All right, we continue with the lecture. So we have from now 20 minutes until the end of the tutorial. Please go ahead.
Okay, great. Okay, so I told you about these two measures of correlation, this maximal correlation and hyperconjugative ribbon, which satisfy the tensorization property, and then some variants of the hyperconjugative ribbon, the relation between them. Now I want to tell you about some applications. In fact, I'll be talking about two applications where both of them are related to this nonlocality and generalization of that. So let me tell you what the nonlocality problem is. So we have these two parties, Alice and Bob. Each one of them has an input, X and Y, and then they are shared classical or maybe quantum correlations. And depending on the correlation and the inputs, each one of them applies a measurement and then determines an output. Like in the quantum case, and Alice would be a measurement setup. It's a label of a measurement that she applies on this subsystem that she has shared with Bob, and then the output of the measurement would be just this output A. Or it could be like the classical correlation, and then in which case this is a label. It's some little, it's like a string of zeros and ones, and then Alice applies some functions on X and this thing that is shared between Alice and Bob, and then determines the output. And similarly for Bob. Then the whole thing would be a conditional distribution of this form. Given X and Y, we have a distribution over A and B, okay? And we are interested in this kind of distributions, these conditional distributions, PAB given XY. And the question is that what kind of distributions, such conditional distribution can be generated in this setup? And of course, the answer depends on the physical theory. If we have a classical theory or in fact a local hidden variable theory, then this conditional distribution can be written in this way. That's where lambda is essentially this shared randomness. In the classical case, it's a shared randomness. It has some distribution, and then Alice applies some function on X and lambda, the shared randomness and X, and then determines A that's captured by this conditional distribution, P of A given X lambda, and the same thing for Bob. We multiply all of these things and then take the average over lambda. So all distributions that can be written in this way, these are the distributions can be generated in the classical case, when the source is the classical source. In the quantum case, this source is shared state, it's a quantum state, which I denoted by this vector psi. And then these are the measurement operators of Alice and Bob. And then when you compute the sandwich, you get this joint distribution, this conditional distribution. So in quantum case, the distributions are realizable in the quantum case if they can be written in this way, where M and N are POVM elements. In this talk, I'm interested in distributions. I want to put the minimal amount of assumptions on this distribution. And the answer, and one of these conditions, one of these famous conditions, is the no signaling condition. The point is that if I ignore the output of Bob, which means that if I take the marginal of the output of Alice, which means essentially means that if I sum these numbers over the choice of B, if I compute this thing, the no signaling condition means that this conditional distribution is independent of Y. So it depends only on X, not Y, which makes sense because, you know, I mean, think of the quantum case. We have something shared between Alice and Bob. Alice applies some measurement and then takes an output. The output of Alice depends only on her choice of measurement and does not depend on Y. Otherwise, Bob could signal to Alice by making different choices of Y, right? And the other way around. The margin of what B should be independent of the measurement choice of Alice. And that's the other no signaling condition. So here, I want to restrict myself to set of correlations of this form, which satisfy the no signaling condition. If you think about that, if I, for example, in this expression, if I marginalize over B, if I sum over B, by normalization, this term disappears. And I don't have a Y here. That's why I have a no signaling condition. In the quantum case, if I sum over B here, then by because these are POVM elements, the summation of these things over B would be independent of Y. In fact, it would be the identity. And then there's no Y here. That's why I have the no signaling condition. So no signaling is a natural condition that I want to put on the space of these things. And the other thing is that in the following slide, I put a box instead of Alice here and another box instead of Bob here. The point is that I don't want to care about what happens inside the box. I want to think of this really as a box that has an input and an output. And the Bob side, I had another box which has an input and an output. And probably this line between the two boxes show that they are probably correlated with each other in some sense. And the question is what kind of correlations are realizable? Okay. Okay, so I have this box here, we have this famous example of the CHSH game. The question is that if we choose X and Y completely randomly at uniform, what's the maximum probability that the XOR of the outputs is equal to the multiplication of the inputs? So in this example, X and Y, A and B are, each of them is a single bit, takes values either 0 or 1. And then the question is that what is the maximum probability of XY to be equal X A plus B mod 2? Okay. In the classical case, this maximum probability is 3/4. Why is it the case? Because if you consider the 4 cases that X and Y can take, like 0, 0, 0, 1, 1, 0, and 1, 1, these are the all cases that the pair X and Y can take. For 3 of these 4 cases, X times Y would be 0, right? So if we choose A and B to be 0, independent of the inputs, so like Alice ignores what X is and Bob ignores what Y be, and always output 0 and 0. In that case, this inequality is satisfied. Sorry, this equality is satisfied for 3 of the times, right? Because 3 of the times, of the 4 times, X times Y would be 0. So that's why in the classical case, we can with that easy strategy, Alice and Bob can take this probability to be 3/4. And you can show that this 3/4 is really the maximum. They cannot do better than that. Okay. And in the quantum case, we can do better than that. I won't tell you what the strategy is. You probably, all of you have seen this. This is a context of Bell inequality via this CHSH game. In the quantum case, we can get to this number, which is strictly greater than 3/4. And that's the content of this Bell's nonlocality. And it says that in the quantum case, we have correlations that cannot be realized in the local hidden variable model. But what about in the no signaling case? Of course, I can get this number because the classical case I have, in the classical case, I have the no signaling condition. Similarly, in the quantum case, I have the no signaling condition. So I can get this number if I restrict myself only to no signaling correlations. But surprisingly, if I put only the no signaling condition, I get 1. With probability 1, I can satisfy this equation. Why is it the case? I can give you a distribution, a correlation that satisfies this this equation. It's simple, it's easy to guess. The probability of A and B given X and Y. Check if this equation is satisfied. If it was the case, then let this probability to be 1/2, and otherwise let the probability to be 0. The point is that if you fix X and Y, okay, then A and B can take for cases, like 0, 0, 1, 0, 0, 1, and 1, 1. And for 2 of these 4 cases, this equation holds. Put the probability uniform distribution over those 2 cases, and then take the probability of the other 2 cases to be 0. Okay. And now I have the no signaling condition because if you marginalize over like A, the marginal over A is uniform, because like if X and Y are both of them are like 0, the product is 0, then we have this equality for A and B being 0, 0, and 1, 1. So the marginal over A would be uniform. With probability 1/2, A would be 1/2, with A would be 0, and probability 1/2, A would be 1. So the marginal over A is not only independent of Y, it's independent of X as well. And it satisfies the no signaling condition. And this is called a PR box. Okay. Now, I want to talk about the more general PR boxes where I want to put this parameter lambda that I had before. So I'm defining P of lambda to be given by this thing. If this condition is satisfied, I take the probability to be 1 plus lambda over 4. And then if it's not satisfied, I let the probability to be 1 minus lambda over 4. It's the same distribution that I considered before. For example, if X and Y are 0, it's exactly the distribution that I had before. And by the same kind of reasonings, it's again a no signaling box for any choice of lambda. Okay. In particular, for lambda equal to 1, it's the perfect PR box that I had before. And if you make lambda larger, you will get a more non-local correlation because, for example, here it's clear that for lambda equal to 1, we get the perfect PR box. It is highly correlated and saturates that CHSH inequality. Now, the question that I want to ask is the distillation problem. The question is that given some copies of this P lambda, this box P lambda, can I simulate a box with a larger value of lambda? Okay, so that same distribution simulation problem, but for boxes. Okay, I guess I should move a bit faster. What do I mean by simulation? The simulation is given by wiring. Suppose I have 2 of these boxes, and then the idea is that I can wire the output of one of the boxes to the input of the other one. I can choose some function, and then the function would tell me what would be the input of the next function. That's the wiring, and Bob does the same. Then I can think of the whole thing as a new box, which has an input and output, and the Bob side also has an input and output. Okay, so this is a wiring of no signaling boxes. Or they can do even this kind of wiring. So these are 2 boxes, box 1 and box 2. Here, the wiring always first uses the second box, and then wire the output of the second box to the input of the first box, and the other way around. Okay, so Bob does the other way. So they can do this kind of weird kind of wirings, but the whole point is that these are essentially these wirings are local operations on the space of boxes. Now, as I said, I want to ask if we can start with some arbitrary number of copies of p lambda for a lambda that is less than mu, and simulate one copy of p of mu. So like this still non-locality, but under wirings. Okay. This means that I need a measure of non-locality that satisfies the tensorization property. And this is my measure of non-locality. It's suppose this is my box with input x and output a and b, and the maximum. I define my measure of non-locality in terms of the maximum correlation that I had before. So I define a maximum correlation for non-signaling boxes, and the definition is of this form. I choose a value of x and y. It induces some distribution between the outputs, and then I compute the maximum correlation between the outputs. And then I take the maximum over all choices of the inputs. So the maximum correlation of a non-signaling box is the maximum of the maximum correlation between the outputs over all choices of the inputs. Okay. For example, if I consider this, sure, yeah. For example, if I consider this kind of generalized PR boxes, the maximum correlation would be lambda as before. So I should be a bit quick. The whole point is that I have a data processing type inequality for the wirings of non-signaling boxes when the measure of non-locality is measured in terms of maximal correlation. I don't have time to go through the details, but the point is that I have some sort of a non-locality which can be proved using all the previous tools that I had, or I told you before that all the properties of maximal correlation can be proved using Cauchy-Schwarz, and this is an example. I'm not going to go through the details. And then I can use this lemma to inductively say something about the correlation of these boxes when I wire them together. But more general kinds of wirings cannot be handled by this lemma. Okay, it's more complicated than that. But the point is that this is still true. If I start with some copies of this box PAB given XY, wire them together in any arbitrary way, even random kind of permitting the boxes and then wire them together in a random way, and then generate the prime box, then we have this monotonicity when I compare the maximum correlation of the boxes together. You can look at the details here. I will skip over these things. You can also prove this the hypercontractive ribbon for boxes by the same kind of ideas, and again you have the same theorem. The monotonicity under wirings, you have the same thing. I guess I don't have time to go through the second application, but it's again about this non-locality, but non-locality in networks instead of just of two parties. You can consider lots of parties which probably some of them share some sources together and then try to generate some distribution. You can again ask about the separation of the quantum and the classical case and things on that. The only point that I want to say that there's some linear inequality that you can apply in these kind of networks that are related to this hypercontractivity inequality. So let me skip these things, but you can look at this paper, for example, to learn about this linear inequalities in its quantum version, and also to this paper for an application of this linear inequalities and things like that on non-locality. So let me summarize. I told you that the tensorization property appears in lots of source and channel coding problems. So it's natural to and find and search for measures of correlation with the tensorization property. And some of these problems I told you about, this non-interactive distribution simulation, simulation of zero capacity channels. This is in fact a classification problem in terms of classification of different channels, and also in non-locality. The point is that in non-locality also, when you ask about the limit of non-locality, you don't care how much like randomness or entanglement is shared between parties. So that's why you get you need a measure with the tensorization property in order to characterize non-locality. I told you about the maximal correlation and also the hyperconjugative ribbon, and we saw different features of hyperconjugative ribbon and its relation to maximal correlation. And I briefly told you about two applications. Both of them are in terms of are about non-locality. What about open problems? One problem is this tensorization problem. I told you that tensorization property for quantum measures of correlation is an easy problem. Exactly because of the same difficulty, the difficulty of additivity in the quantum case. Like we know that the Hollow capacity of a quantum channel is not additive. Like we know that the coherent information of a quantum channel is not additive because of the same kind of difficulty that we have. And we learned that the additivity is a dual of the tensorization. So the tensorization is also a big deal in the quantum case. So because we have lots of additivity problems and additivity conjectures in the quantum information theory, similarly we have lots of tensorization type questions in the quantum case. The other thing is that, as I said, computing the hyperconjugative ribbon in general is a hard problem, but there are some tools in the classical case for computing it. In particular, the log subtle of inequalities. So in the quantum case, log subtle of inequalities are also useful tools for computing these hyperconjugative ribbons. And that's why quantum log subtle of inequalities are another subject of interest for me. I guess a natural question to ask is a measure of entanglement with the tensorization property. I didn't put a reference here, but at some point I tried to generalize this definition of quantum maximal correlation to make it a measure of entanglement rather than just a measure of correlation. But the definition works. It satisfies the tensorization and the monotonicity properties. But the problem with that definition is that it's hard to compute because it is in terms of some, as you can guess, to go from a correlation measure to an entanglement measure, you go to like different decompositions of a density matrix into a pure entangled state, and then like in the entanglement formation, you take a convex roof type kind of things here. You can do the same kind of things to get a. And finally, a measure of correlation for channels that satisfy the tensorization property is also very useful. In particular, I told you about the maximal correlation for no signaling boxes. And the no signaling boxes, if you think about that, there are channels. There are two-way channels, two inputs and two outputs. And the no signaling condition means that the capacity of those channels are zero as two-way channels. So, and then the question is, can we have such measures of correlation, in particular for quantum channels? Because in that case, we can solve that problem of simulation of zero capacity quantum channels. Okay, by this I'm done, and thank you very much.
Thanks very much. Before we go to roundtable, I wonder if you can answer a quick question. It has to do with hypercontractivity ribbon, and it asks whether it can be an unbounded set.
I guess I didn't understand the question. Would you please repeat?
Okay, sure. Why is the hypercontractivity ribbon a ribbon? I mean, it seems to be unbounded. Can it be unbounded?
Yes, it is. Yes, it is usually unbounded. Yeah. For example, if you consider this this example, let me go back to this example of the Bonomi-Becker inequality. Yes, yes, this one. As you see, this is unbounded. And I think it's usually unbounded. So it's not just of, for this kind of distributions. In general, I think it's unbounded.
Can it also be empty?
Well, depends on the definition. If you consider the non-trivial part, yes, it can be empty. For example, if you take lambda to be 1 here, then it collapses to a single line, which gives you the trivial part. So yes, it can be empty. Yeah.
Okay, thank you very much. Thank you for the great tutorial. Everybody now is invited to join us in the roundtable, especially those of you who had questions and we couldn't address the questions. So we will see you in the roundtables. Thank you very much.